Hello, everyone. We're going to be going over EE301 for the final review. So what we're first going to start with is finite state machine analysis. And so let me just write that here down. So let me get my editing options available. So for finite state machine analysis, we're going to be going through what's the basic process that make it up. So let's look at just an example. So I'm going to draw out a circuit for you guys. And so here we have an AND gate, and then we got two others. And then we have an OR gate here. So we got two OR gates. And then we're going to have our D flip-flop. If you guys remember what those are, basically the output is the same as the input as long as it's at the active clock. And so that's why we like to use our D flip-flops here. And then we have the output, and we also have the output bar. And so that would give the opposite output. And then at the end, we have another gate, which is the AND gate. So let me just do this D flip-flop here, and then let's do an output Q and then Q bar. And then our final gate here. So when we're looking at this, what we're going to have is for my finite state machine, I'm just going to make up a combination how all these are connected, and we're going to analyze it and see how it be built together. So for my example, let's just have this one connected here, and we'll connect the Q bar. So let me jump it over and connect that back here to the first AND gate. And then I'm going to connect this one, the Y, also downwards here to the bottom AND gate. And then we're going to have an input W. So this is a serial input. This would be what the user inputs to the device. And I'm going to connect that here to these three AND gates. And then now I'm going to do the Y2 outputs. So right up here, we have Y1, and then this D flip-flop output is going to be Y2 because it comes in the second order. Let's put this back. Okay, so Y2 here. And then our other one, it's going to lead to this output gate here. And then what we need to remember is for the D flip-flops, they have clocks. So I'm going to just draw this in another color just so you guys recall. The flip-flops, we have clock inputs to them. So they go on the active clock. And so for my input here, I'm just going to say clock. And then remember, you need a reset. The reset on flip-flops is always asynchronous. And so it's always active low, so you guys recall. So just remember those inputs. They're easy to forget to include. And then, so I'm going to call that reset N here, and then put that up. Okay. Now that we got the clock and the reset in for our flip-flops, and we got the outputs, remember there's also inputs to those. So real quick, let me just draw a line here connecting the two. So let me go from here to here, connect it. Let me just draw that actually real quick. So connecting this output to this one gate and then this output here. And then for my other one, I'm going to connect this output to the other gate down here and this output here. Okay, now for D's, it's going to go straight to the flip-flops here. So flip-flop in, and then straight to flip-flop. Okay, now we can actually analyze. So we finished doing it. So real quick, I want you guys to say, is this mealy or more tight? That's the big part. When I'm looking at this circuit, I'm like, okay, so we see the output here is Z, and I'm looking, is there any inputs that go back to any outputs here? So like any of the inputs to the last stage that come from the input by the user. And when I'm looking at it, I'm like, no, this has to be more type. If it was mealy type, basically I would have to have something going from the input here, and it have to be connected to this gate for the output. so would influence the output variable here. However, there is no connection, so I can determine that this is a more type because there is no connection from the user input to the final gate. And then what I need to look at is we need to analyze all the outputs because that's significant when we're trying to determine how many states there are and to find our equations. So in order to determine the outputs, what I would do is I would go through and label all this. So in a smaller little, let me decrease the size, not make it as large. So here I'm going to just say this is y1 for my first state variable, and then this is y1 bar here. And so I'm just going to do an exclamation point in front. Here is y2, and then down here it is negative y2 with the bar on top. And then over here, I like to just label everything. That's what you need to do in order to do well. So label all these inputs to the gates. And then we notice this is from y1 here, and this one was from not y1, and then here we had y2. And so looking at the gates, we know the AND gate, it's going to be w times, and then the not of y1. Here it's going to be w times, and then y2, and then here it's going to be w times y1. And then when we look at now the inputs here, we see that at this OR gate, it's going to be w times, and then the not of y1, and then plus, and then w times y2. And then down here, it's going to be let's look at it real quick. It's going to be w times y1 plus w times y2. Okay, so we got the inputs, everything's determined here. And then here at the output, all we need to say is it's y1, and then here it's y2. So now when we're looking at this on the actual side, besides just determining that is a more type, this finite state machine, we need to look at what's going to happen for our states. So the biggest part here is you need to see that, oh, okay, we got two flip-flops here. So I got one and I got two. So we have two flip-flops. And so that tells me we have two state variables. You guys saw y1 and y2. And so that means we can have four states. And so what does the four states mean? Basically, if you guys look at it, you guys will have the present states of y1 and y2, and then the next states, which is capital Y1 and Y2. And so here, I'm just going to write that down so you guys remember. Y1, Y2 is your present states. Y1, Y2, that's going to be your next states. So there's your four states. You have basically your two state variables, and you can have two states for each of those state variables. And so now we're going to want the equations. So we need to find equations for Z, Y1, and Y2. And you're probably wondering why these three variables. We'll look at it and tell me why. So if we see Z is an output, so we want an equation for our output, and we want the equation for the next state. And those are determined by the present state. So those are what are determining those outputs here and next states. So what we're going to do is we see that y of 1, so big Y. So if we want to just make equations real quick, y2, y1, and z, basically, when we're going to make these equations, what we need to look at is our diagrams and see what did we develop. Well, when I'm looking at this, I know z for sure is y1 ANDed with y2, and we can tell that just by the diagram. And then for big Y2 and big Y1, if those are the next states, if we're thinking about it, it's determined by the present state. And so if we're looking at our flip-flops here, basically the output is going to be our next state, but we're coming in with the present state, correct? So here we have the present state, And then our flip-flop is going to determine the output, which is the next state here. And so the inputs to each of these, if we look at it in the equation for y2, that would be the second flip-flop down here. The input, if we're looking, it's w times y1 plus w times y2. And we can just simplify this. And so it can be w and then times y1 plus y2. So y1 plus y2. And then for our next one, for y1, if we're looking at this, the next state, it's determined by the present state here, which is w times and then y1 naught, and then plus w times and then y2. We can simplify this. So it's going to become w times y1 naught plus y2. Okay. Now that we've received those three equations here, we're going to be able to make a truth table. And that's going to be important for ours in order to go back to the actual table here. And so I'm going to make our values. So let me go through and show you guys how it works. So right here, I'm going to draw a table. And so we have our inputs, which was W, you can tell. And then we have our Y1s, small y1 and small y2. And so that's what I'm going to determine as my inputs. And then our outputs are these three variables here, the next states and the output. So let's write those in here. So we have small w, then we have small y1, small y2. And then for the order, though, you guys are probably wondering, which order should I put this in for my truth table? Well, for your truth table, what you should do is, if we're thinking about it, let's start it with y2, then y1, then the serial input. Because the input, we can change that up from 0 and 1. And then for the other two, y2 and y1, we'll start at 0, 0, 0, 1, and then just keep going up from there. We'll see. It really doesn't matter. You can put it in whatever. Your output is a little more where it might matter about. But as we can see, the reason why I use those three input variables is because look in here for y2, you have y1, w, y2 determining it. And then for y1, you have w, y1, and y2. So those affect these two outputs. However, for z, we need a different truth table since w does not affect it. Okay, so let's start out. So if you guys remember just the normal truth table, start with all your values and go up from there. Okay, so we got our values here. And we need to look what our output's going to be. So to determine our output, what we need to do is we would plug it in here. So whenever we have W0, it's an AND gate here. So it's basically going to cause this expression to always be false. And that is the same here. So whenever it is 0, it's going to cause both outputs to be 0. And then whenever W is 1, then we have to loop inside here. However, you guys can do that on your own time and evaluate it. So I'm just going to give you guys the values. Okay, now that we determined that, we found out what's happening. So now we need to determine the truth table for Z. And so remember Z, it's only affected by small y1 and small y2, the present states is seen by the equation. So here for my Z, I'm going to just have y2 and y1. Okay. So 0, 0, 0, 1, 1, 0, 1, 1. And for my Z output here, if we see they both have to be true for this to be false. So this is what I get here. Okay. Now, what we have to do is remember that state assigned table and then the state table in the state diagram where we started back from. Well, right here, you have your truth table. So now we have to go back and put this all together. And so going backwards, what we have to do is I'm going to draw this up in the right-hand corner just to keep it on the same page. So let me move this over. For a state assigned table, You guys remember it's based off the present state, next state, then output. So we have our 3 columns here. We have the present state in the first column, the next state in the second, and then the output in the third. And so when I'm going here, I'm going to do the present state. So I have y2, y1. And then for my next one, I have the next state where I have, and if you guys recall, it is based on your serial input, and then you have your big y2, y1. Then for the other one, you have your y2, y1 here. And then for your third, this is the output. And for output, it's just z. And what we basically have, if it was Mealy type, we would have W0 and W1 here. Because the output would be determined by the serial input would be one of the influencing factors here. However, it is not. So for output, we just have the 1 for Z, this one column. So transfer the table over. So here for the present state, if I'm thinking about transferring this over, I think the easiest thing to do, we know the output is 0, 0, 0, 1. So that's the easiest thing to transfer over here. So we can just put 0, 0, 0, 1. Okay, looking at the next state. Well, when was, for our present state, we know it's 0, 0, 0, 1, 1, 0, 1, 1, just following the common terms. And then now we have to pair these together. And so when I'm looking at this, we have to go through that truth table we created. And what I have here is see how there's 0, 0, 0, 0, that matches up 0, 0, and then our W was 0. And so then my Y2 and Y1 were both 0, 0. So here I can put 0, 0 for that. Here it was 0, 0, and then when my W is 1, looking here, 0, 0, my W is 1, that was 0, 1. And so here I can write 0, 1. And then my next one, it was 0, 1, 0. So 0, 1's here, and then our W is 0. So that produced an output of 0, 0. So I can write 0, 0 here. And then it was 0, 1, 1. So looking here, 0, 1, 1, 1, 0. And you can see it's just going to go down there. So I'm just going to copy the rest over, keep doing that same order routine. And then you're going to get all your specifics that you need. 1, 0, 0, and 1. Okay. So now we determined all of the specific next states. And now that we determined those, we have to assign a state to each of these. Well, if you guys remember, when you're trying to determine states, remember the reset state. That should always be your first state. I like to stay in order specifically. And so I would start here just with A, I would start with B, and then I'd start with C and D. I just find that the easiest. And then if we just label these accordingly, A, and then label these on the side here, 0, 1 was B, and then 1, 0 was C, and then this was B, and this was C. Okay, so we got all the states here. You guys already labeled all this. You know what you're doing here. And now you have to make the state table. So we basically went from here where we had the state assigned table. And now you're going to do the actual state table. And so down here, I'm just going to do my state table right under it to keep it in order. So the state table, just so you guys can see how it looks compared to the first, it's going to start with the state. So just replace it with everything up there. So let me just draw another table line here. And similarly, it just has the present state, if you guys recall. Then we have the next state. And in our next state, we have the W equals 0, the W equals 1. So I'm going to write that here, W equals 0, and then W equals 1. Okay, and then we have our output. So same, it looks pretty much similar. The only difference is that we don't list the next states like the Y2, Y1, because we only have one variable in here for states. Just here, we only have the variables for the state. So it only takes up one column. Okay, now for our present states, just labeling those, we have A, B, C, and D. For our next states, here we have A. And then for here, for when it's 1, we have B, C, D, D. And then for our outputs, looking here, it's still 0, 0, 0, 1. Okay, so now you guys got the state table. Now the only thing, remember working backwards, is that state diagram. So if you guys recall that, now we have to make the state diagram here. And so what we're going to do is I'm going to try drawing that just in the left-hand corner to try and keep everything in the same place. And so if we remember state A, and then I'm going to have state B, and then I'm going to have state C, and then I'm going to have state D. So I'm going to have my 4 states here. And then I'm going to start with reset. And for reset, to make sure, look here, when you're 0, 0, that's going to cause this one to clear and this one to clear as well. So the output is cleared. So reset starts with state A, where Z is 0. Let me just clear this up. And so we have A where Z is 0. And then for our state, we'll see if if W is 0, our input, then we're going to remain in A. But if W is 1, we go to B. And so in order to make that work, so here I'm going to just go A to B if W is 1. So this is when W equals 1. Then we're going to go to state B. And in state B, you can see the output from the state table, Z is still equal to 0. Our other state was C, where Z was equal to 0. And then finally in D, where Z is equal to 1. And so those are my 4 states here. And then keep going, sorry. When we have W1 for these, it's going to go to C. And then when W is 1 in state C, it's going to go to D. And then if W is 1, it's going to remain in D. And so then now we're going to look at the case where W is 0. So we determine if W is 1 here, it goes to B. W is 1 in state B, it goes to C. If W is 1 in state C, it goes to D. And if W is 1 in state D, it remains in state D. Just following the outputs here, what it says for your next state. Okay, now that we determined that, we're going to look if W is 0, you remain in state A. That's what the diagram told us. So here I'm going to say W equals 0. And then in state B, if W is 0, you go back to A. It's basically just follow the columns here and you should be fine. So following this one here, and then this one here, and in state C as well, there should be all your cases where W equals 0, where W equals 0, and here where W equals 0. Okay, so now we got all those cases, and we have our reset N here properly, and we have all the states, and we have all the proper transitions. And so you are good here. Let me show you guys what it'd look like if we basically have the mealy type. So the changes, I'm going to just show you what it would look like in, let me do it in brown here, just to differentiate it. So if we were in brown for the mealy type, what it looked like on our state diagram, there would be a line connecting the final output to the input W. For present states, you guys would have here a column for W0, a column for W1, and then because it does influence the output W, and then we'd see in our state table as well, there would be 2 outputs here for W0 and W1. And then remember, you do not determine the outputs for mealy types in the states. It would actually be with the specific input. So you'd say like Z equals, because it's determined by what your input is for W. It's not within the state. And so you'd have to do that for all these here, tell me what Z is equal to. And then also, if we're looking back at our original table here, we would have W affecting the output Z. So we would have to have a column for W in just our state table, sorry, not state table, our truth table down here. So this big process might look scary. It's just going backwards, what you guys need to do. And so let me just list out the process here. So what I would say is analyze the state diagram. Remember how I was drawing all over it and I was just trying to see. Then after you do the find out how many state variables. That's basically number of flip-flops, aka. So after you find out how many state variables you have, you need to make equations for the outputs. And so that's what I did here, y2, big Y2, big Y1, and Z. The next states and the output Z. Then you're going to make the truth table. And after you make the truth table, you make it for each one. So you make it for Y2, Y1, and Z. Then after that, you're going to make the state assigned table. And then you go to the state table. And then you make the state diagram. Okay, so that's all your processes of how to be successful and do the analysis correctly. And so that I would just follow those simple rules there, and you should be good for the actual exam for analyzing a finite state machine. And so, sorry, that's all on one page, but I just wanted you guys to see everything at once. Now we're going to get into the next thing on the final, which you talked about reviewing, which is the ASM chart. And so we need to review what an ASM chart looks like. Okay. So let me clear everything real quick. Okay, so ASM chart. What does that look like? So basically, the reason we use an ASM chart is because it's for larger finite state machines. And we basically have 3 elements in an ASM chart. And so what you guys need to keep down in your mind is that we can have these state boxes. And so the state boxes, it will say like state 1 here. I'm just giving you an example. And then it would have an input to it and an output. So input and output. And it would say the output signals or actions. And so this is usually, I do better when I just see what would go inside of it. So usually what you would put inside here is like your Z term. That is one common example for your output. So like Z equals 0 or Z equals 1. It depends on, so you can see this is more type because you actually assign it within the state, the output. And so that is your state box here. So I'll put that right above. And so you guys know this type here. And then for your next one, you can have a decision box. For a decision box, it basically is a diamond shape. So let me pull that. So your diamond looks something like this. And you basically have a condition expression. And within this condition expression, it can either be true or false. And so here, it can either go to one or the other. And so if it's determining if it's true or false, this is a pretty important one. You'll use it a lot to go from one state to the other. And so I'm going to label this 1 as true and 0 as false. And basically, you'll have your input here, so it can determine 2 factors to go in one path or the other. So maybe if you want to do addition or subtraction, one or the other. So that's what it determined. And then the next one is a conditional output box. And so for your conditional output box here, what is going to be inside of it is you're going to have your conditional outputs for actions. And so this is your mealy type. And so that's where it's dependent. So let me just put this in there. I'll just put So a mealy type, if you guys want to see what actually would go inside this, because it's better to see, for your conditional output, it can be something like if this is triggered, so let's say like the condition was true, then it could be like z equals 1. So let's say like this was your input W here, your conditional expression, W the serial input, and if it was true, then it would say Z is equal to 1 here. And so this is for your mealy type. It says it with after the action takes place, it just states the output in the diagram. And so what I'm going to do for that one, let me just label that as well. And so you guys have the 3 boxes, and this is how you determine which one to use for your specific finite state machine. Basically, if you're working with a more type, you use the state box, and right inside of it, the state. If you're working with a mealy type, you have to have this conditional output box to determine your outputs. And so those are the important ones that are pretty significant, I would say, compared to the others. And so now we're going to look at digital systems. And so looking at digital systems, what they are and why are they important. So basically a digital system consists of 2 main parts. And so we have a data path circuit to store and transfer data between system components. So what do you guys think actually stores and transfers data between one thing to another? Well, if you think about it, like registers, they're able to shift or they're able to like parallel input all the data at once. So that's one type. And because you can have the shift or parallel feature. You can have counters. Counters are basically like they will just like add 1 to it, so they can like store, because they store the previous and they just add 1 to that, and then it changes the value, so like they keep memory of how many counts there's been. Multiplexers. Multiplexers are like decisions, and then it determines the output based off that specific select signal in there. Decoders, which can decode data, and that's an important part. So for your transferring of data. And then the other one is going to be your control circuit. And so this is a finite state machine to control the operation of the data path circuit. And so those are your 2 types of circuits. You have a data path circuit, which stores and transfers data between system components, and you have a control circuit, which is a finite state machine. So to control the operation of the data path circuit. So we're going to look at both these and see what they are. So I'm going to do the 2 examples he did in class, just because those are the only ones we went over. So those are the ones that he's probably going to quiz you on. And so let's do an adder. Okay, so let me pull this up real quick. So for a simple calculator that does addition. So what we want to do here is we're going to want to add 2 4-bit numbers. I'm going to say A and B and display the results on the LEDs. So you add them together and then it will show. So like 0, 1 plus 1, 0 equals 1, 1. So those 2 LEDs would be on. Then we're gonna use the left 4 slide switches to enter the value for A, and the right 4 slide switches to enter the value for B. And then within this, so if we're using slide switches to enter the value for A, that basically means like our A has 4 bits in it, and the right 4 slide switches enter value for D because that has 4 bits. So we need 4 slide switches. Okay, now that we determined that, we're going to need to do 3 types of actions we need to add, we need to clear, and we need to reset the calculator. So like, if we think about it, add would be A plus B. And so that would be displayed. For AC, that would mean that it's basically 0, the output. So here for the output, I'm just going to say the sum is equal to A plus B. Here for the output sum, it's going to be equal to 0. And then for the reset, that's like if it's turning on, let's say, and it just wants to clear everything, that'd be the sum is equal to 0. Okay, now that we have determined all those, let's look now at our algorithm and states. And so the first thing is, if we want to think about it, the sum is immediately changed the output based off the inputs here. And if I'm looking at this, how would I determine if it's a meal or a Morley type? And so what we're going to see is that we remember the Mealy, the inputs can determine the output like at any time, but the more type is when basically it's all those specific, and that all the inputs, they go through like combinational logic, and then it determines the output. Well, here we're going to see it's the more type, but in order for it to make more sense, I'm going to continue with it, and you'll see why specifically. So first, let's start with our algorithm. Oh, let me just close that real quick so we don't hear any noise. And so for our algorithm, let me write up what we have here. And so specifically what we need to do is we need to determine our specific input. So we have reset, we have AC, and we have add. And so for reset, we know that the output sum is going to be equal to 0. For AC, we know the sum will equal 0 as well. And for add, we know the sum will be equal to A plus B. And now we need to determine our state. So specifically, we notice that when we are in reset, that's when we do power on because it clears everything on the screen and it starts from the beginning. So that's specifically for a reset function here. And for the rest of these, we have to determine the state. So here for our sum 0 and here for our addition here. And then what happens if we don't press any addition, we don't have any clearing, because those are the only two we can do after it's on. So those are gonna have to be in another one. So maybe we don't hit clear, maybe we don't hit add either. And so the sum would just be, if we don't hit anything, there's gonna be no change in it. If we don't hit anything for addition, there's gonna be no change in it. And so now that we determined all those, for reset and add, that's going to be starting state 1. For the addition of the 2, that's a different state, that's state 2. And then for if we press neither, that's going to be state 3 because there's no change. So one we have where the output's 0, one we have where it's the addition of the 2 numbers, and one we have where there's no change in the output. So therefore we have 3 states. And so if we have 3 states now, we can determine going to our specific ASM chart and actually figure out how to draw this out. So remember how I said, whenever you hit, I'm just going to start from the very beginning. When you hit reset, that means that the power is on. So you're immediately going to clear. And so within our box here, I'm going to represent this as state 1 here. So within state 1, you hit reset, and basically what we determined here is the output sum is equal to 0. So that's our output. Because it's a more type, the output has to go within the state box. And then what's going to happen after? Well, if you think about it on a calculator, you're going to hit, it's going to decide, did you press or not AC? It's going to be continuously checking. Did you press the clear button or not? Did the user press any addition button or not? And if they did press basically addition, or if they did press clear, it would go to then that respective output state. However, if they didn't, it would go to state 3. So let's look at it and let's see what happens. So basically, when I'm going to the next one, I'm trying to think clear or addition, which one has higher priority? And clearing has higher priority just for this scenario. We always know clear is usually our top one that it should be checking for, because whenever it's clear, it should go back to the beginning. So that's why in here, I'm just going to label this AC. And then for my other one, it's going to be the addition of the two. So I'm going to label this add. And then we're going to look at the specifics when it's 0 and when it is 1. And so here what I'm going to do is for the AC, when it is 0, we know that then we didn't press clear, so it can go to addition and check to see if the user pressed addition. However, if the user did press 1 for AC, that means clear everything. So then if we cleared, that means it would go back to state 1. So here I'm going to draw my little arrows going from the one state to the next. So here we go. And it would go in this direction here and start back at state 1. However, if you didn't press, it went down to addition. And now we need to determine, did the user press addition or did they not? So if the user didn't press addition, that means they also didn't press clear. So it's going to go over to the actual state 3, where the sum is still equal to 0. Sorry, not sums equal 0, sums equal to no change, because they didn't press any button. And so here, when I draw it out for my state, and remember state 3, I gave it for no change here. So when I said sum is equal to no change, this is my state 3. Okay. And then my other state, if the user did press addition here, then we would go to state 2, where it would be the addition of the two numbers. So going down here and drawing out the box. So this would be state 2, where the sum would equal A plus B. And so this would be our state 2. So we have all the states labeled: state 1, state 2, state 3. Now, from state 3, no change. Now it's going to go back and check again if the user pressed AC or add, because it's going to be continuously checking. So we're going to have our 2. So remember, AC had higher priority, so it's going to come first. And what we're going to see is if the user did press clear, so it's going to check this after the state. If the user pressed clear, then it's going to go back to state 1, correct? However, if the user didn't press clear, so if they pressed, let's say, we don't know what they actually then, because nothing's happened, so we don't know if they pressed anything yet, but if they haven't pressed anything for the clear, then it's going to just go back and check, did the user add anything? If they added anything, then add them the two together. And so what's going to happen is we're going to see is, I can sort of simplify his diagram, is if the user press clear and nothing happened, then we can just go back and check, well, are we going to do addition? So, oh, oops, no, it turned out right. So I can go back in here and I can do addition and check to see if the user pressed addition. And so then we'll see. And then if the user didn't press addition, it goes back, check, did they press clear? No, went back to addition and then went back here. And so it just simplifies the process a little. And then in the addition of the two, then it's going to check, did the user press clear? Did they press add again? Well, then if we're going up here, we're going to see, actually, we can simplify this almost even a step further if you really think about it. Just look here. What we can do, oh, oops, did not mean to clear up all that, is if after it goes for the no change, if we go immediately back to check if it's clear add, and then here also for the sum, we can go back and check after the state, did the user press clear or did they press add? And so you can go straight back up here. So we can just simplify this diagram very simply, make it nice and neat. So basically we run through all the specific examples here. And so this is a more simplified version, which I like, instead of repeating elements. So if the user hits reset here, then it's going to look at state, it's going to go state 1, clear everything. And then if the user presses clear, it's going to go back to state 1. However, if it didn't, it's going to go to check if they hit addition. If they did not hit addition, nothing's going to happen. So in the state 3 here, nothing happens. However, after that state, it's going to go and check if they hit clear or add again. But if they did hit add, it's going to add them together, and then it's going to check if the user then presses clear again, or then if it would press add. So I like this diagram. It's very simple, so it doesn't involve any repetitive motions. And so now we need to look at the data path circuit. And so for a data path circuit, remember how I told you guys a data path? It's basically storing and transferring the data between the system components, whereas the control circuit is controlling the operation of the data path circuit. So what are we going to have to do here to transfer and store data? Well, we need to add the two numbers together and we need to store that information. And so what I'm thinking is for a data path circuit here, if we need to add two numbers together and we need to store that info, I'm saying that we probably need an adder and a register. So data path circuit, we're going to need an adder to transfer data, add the two together, and then we need a register to store that data and clear data if we hit ever of one of the buttons. And so right now I'm going to draw out my data path circuit and let's look at it. So we have two values coming in. So what we have here is we're going to have our A's coming in and then our B, and then that's going to produce an output for our adder. And then we're going to have the register down here. Okay. So we're going to have A coming in here, B coming in here, and then we pad them with zeros. So zeros are padded here and zeros are padded here because we're doing addition. And if there's ever overflow, say you have 1111 plus 1111, that's going to go over. And so that will account for our overflow error. So 0A, and then here we have zeros, and then we have B. And then within A, it's a 4-bit number, if you remember from the prompt. And so here I put a slash through, and then I say 4 to represent 4 bits. Here for B, I do a slash through and we'll represent 4 for 4 bits. Pad with 4 zeros here. And then for the other one, we're going to pad with 4 zeros. And so then we have our 8-bit number. And then for output, our sum is the addition of the two. So I told you guys that's 8 bits because we're adding two 8-bit numbers together. So here's our sum now down here. And what we're going to do now is determine our register. So for the register, you guys remember we need to have our clock, and there's going to be a reset on it as well. And so we're going to have a clock and a reset. And then we're also going to have a clear to clear the register. You're probably wondering what's the difference between reset and what's the difference between clear. Well, reset is when you hit the power to turn it on, where clear is when you hit AC. So that's why we have two different ones. So we have clear here for the AC. Then we have load, and load is if we hit like the addition of the two, like that's what we want to do. We want to add that sum into the register. And so that's why in our register we have these 4 inputs. And remember, for register you need a clock. And so now that we determined that, so I'm going to just say this is my register here, where the one above was my adder. Okay, so now we did successful addition and we can store that data. And so now that we've done those two, let's determine the operation and control signals. So the operation is determined by the output. And so when looking at this, so our output, we can call that, in this case, we can just do it as, because if you remember the output here from the register, that's going to be 8 LEDs because we have 8 coming from the addition of the two. And so what I'm going to label this, I'm just going to say reg out for my register output. And therefore, when I do the control signals for the operation, it looks at all the outputs. So for reg out here, it's going to be when this is 0, and then when reg out is equal to the sum of the two, and when reg out is equal to no change. And so what we're going to have here for control signals, if you want to think about it, is when the register output is 0, what's going to happen is that means we cleared the input and the loading was 0, therefore we did no summing. Where if we add the two together, that means we did not clear the input, but we did load to do the summation of the two. So we loaded in A and B. Reg out, no change. That means we didn't clear, but we also didn't load in anything because we didn't change the values. Okay, now we talked about the operation control signals, and now we need to make the control circuit. I like the control circuit. It's nice and fun and easy, so that's what I enjoy. So to do our control circuit, what you need to do, I'm just going to draw over the the ASM chart I just drew originally. You basically just fill in your control signals into those state diagrams. And so here, I'm just show you guys, you cross this out in red, you cross this out in red, and you cross this out in red, and you just put what you got here for the output. So here in the first state, it's clear equals 1, load equals 0. Next one is going to be clear equals 0, load equals 1. Sorry, I meant 0 here. And then I was skipping ahead myself real quick. Let me just clear that real quick. Because no change from matching the operation with the control signals. That's what you're doing here. And load equals 0. And then my other one here was clear equals 0 and load equals 1. Okay. Now that we determined all those, and we got our control circuit made, the control circuit, think of it as the brain of the circuit. The VHDL code, you're basically going to have to determine what are the port signals and what are the internal signals. These were always hard for me to know, so I'm going to go through it slowly just so you guys can understand it. So let's look at what are the port signals here. So I'm going to do these in orange. And so everything that I do in orange is a port signal. Okay, so port signals, anything the user needs to provide. So my first thing is like, oh, the user needs to provide the numbers for inputs, right? And so that's why A and B here, let me do that in orange to match it. So anything the user provides, A and B, they have to provide those. The user can hit the button to reset the circuit. And then what else the user does is the user can clear and they can add it. And so they can hit AC or they can hit the add button. And then the clock, this one's a little weird. It's just because the user needs to, the clock is like internally connected with the FPGA. So the user needs to do that. You remember in our labs how we had to connect up the clock as one of the signals. And then, so we got AC to clear, A add, and then we have the clock, we have the reset. then we also need to, the user sees the output. So that's one thing the user is going to see. So those are all our port signals that I can determine where, so we have the A, the user needs to input the two numbers. That makes sense. The user, if they hit clear, so the button on the calculator, they hit add, that makes sense. If the user pushes reset when they turn on the calculator, the clock, the user has to connect up the clock in the FPGA, and the register out, the user is going to look at the output. So that's everything the user does. Now we need to do internal signals, which I thought were a little more. So once you determine your port signals, the internal signals are basically everything else. So here it's going to be, let's just first examine the circuit. Well, it does the addition internally here. So the sum, clear, that does internally in the control circuit. So within these state diagrams, it assigns those values based off what the user inputted here for the AC and the add. So it's just going to assign these. So those are internally clear and load. Does the summation, clear and load, A 8-bit and B 8-bit. Those will be to the others that it makes like an 8-bit number, and it makes a 8-bit number for B because it combines the two with each other. And then one that you're going to forget, and I know it already, is the state variable. You just call it Y for all the state variables. You guys will probably forget that. And so you just, that one doesn't come because you don't see it on the diagram. You see the different states. You got to remember your state variable. So let's go. The A 8-bit is because the computer pads it with 4 zeros. It does that. The B 8-bit, it pads that number with 4 zeros. The sum, it does the summation of the two internally. The clear and the load are done internally as well. And then Y for your state variable. Okay. We have determined all those. We have to now see basically, how do we code this? How in the world are we going to do coding of it? And don't worry about it. It's not as bad as you guys might think. And so I'm going to code this with you guys because he's going to ask a coding question for sure. This is going to be like the one he's going to ask on. So let's go through it together. And so let me put this. So basically, I'm going to just take a picture of this, and then I'm going to stop sharing and just share my computer screen for coding it. So here we go. Okay, let me stop share and reshare. Oh, that was, sorry, from tutoring appointment, not what you guys want to see. Okay, here we go. So I'm going to have this on one side and I'm going to code it on the other. So I'm going to open up my text editor. And let's just look in the beginning what we need to do. So what I always think, well, we have to have a register, and then we have the calculator doing all the processes. And so let's just start from the beginning because this is going to be weird. So remember how I told you guys always start with the library IEEE, and then do use IEEE dot standard dot logic, or standard, sorry, then logic, and then 1164 dot all. And then for the next one, do IEEE for the arithmetic. So the standard logic just does like, you know, like your zeros and ones. So make sure you include that. So use IEEE dot standard, and then here it is going to be logic arithmetic and dot all. And then the other one, arithmetic, is because we're doing addition, we need it. That's an arithmetic operation. And then use IEEE dot standard, and then logic, and then unsigned. dot all. The reason we have to include the unsigned is for the adder, just so you know. So it doesn't matter if you have everything capitalized or not capitalized, because VHDL is not case sensitive. Okay, so let's just look at it. So because this is weird, I imagine, for you guys. So let's just look at the calculator and try determining what we want it to do. Because so for the entity, the calculator is, let's look at all the ports. So I'm looking at my port signals here had A, B, AC, add, reset, clock, reg out. So let me just list all those. So A is going to be an input, and that is standard logic, and then it's going to be the vector. And if we look at A, remembering when we enter that, it's only going to be 4 digits, correct? So it's 3 down to 0, because it pads it with zeros internally. So we only input 4 digits. So then the other one for B, same exact thing. I could actually just say A comma B here, because 2 standard logic vectors, same size. And then we're going to have register out. So the output can be standard logic vector. For my output here, if I'm thinking of it, that's going to be 8 LEDs, right? So 7 down to 0, because in the register output here, we had 7. Remember your semicolons at the end. And then my next one, okay, so I just did AB, I did reg out. Let me do AC in add real quick. And yeah, in reset. So let me just look at these. AC, add, reset, and clock. Those are all just zeros and ones, so they're all the same. So I'm just going to say standard logic, and then that should be it. And so then, oh, remember close, because it's the last one in the sequence. We have to close the parentheses and then put the semicolon. So as you guys see, we just copied over all these port signals right here. So we have A, B, we have reg out, we have AC, add, reset, clock. Okay, so we're good. And that's what I did here. All my port signals are established. And now we have to actually define the behavior of the clock. And so architecture, behavioral of calculator is, and then we need to determine our type, state type is, and this is where you list all your states. So type, state type is, so we have state 1, we have state 2, we have state 3, we have 3 states. And then we have to have signal Y is going to be our state. It's of the state type because it has 3 states within state Y. It has 1, 2, and 3 for the thing. So then we have signal A, 8-bit. And so you're probably wondering, how do I know these are internal signals? I'm looking down here at what I put in. So I have one as Y for the state type, holding all those 3 states. Then my signal A 8-bit, B 8-bit, and then some clear and load are my other ones I need to put in here. And so keep going with it. So I have my signal A 8-bit, and then also I have a B 8-bit, and some is the same size as well. They're all 8 bits. So I'm going to do standard logic vector. And they're all from 7 down to 0. Okay, now that I have determined those, let me go to the next one. So my next internal signal, I got a 8-bit clear and load. So signal clear and load. Standard logic, and then those are just zeros or ones, so that's why we can just say standard logic here. And then now that we finished that, we have to use within our calculator a register component, which makes sense that we're going to have to use the register. And then we also will have to make looking at the rest of it, because looking at the general overview, what I have, we have to name out our entire register, then we have to do our state transitions between each of these. We need to do our actions within those states, so what to assign. And then we'll look at the data path circuit. And so I'm going to go basically off what we have here. So let's look at the component for the register. Why we need to include that? Well, we have a register component in the diagram. Look here, one register. So component register, what I have for my ports here. Let's look at what do I have coming in. So I have clear, I have load, I have reset, I have clock, I have reg out, and I have sum. And so what I need to do for this register, this was already declared in another file because it's a component. So you had to declare that in another file. So these were already assigned basically when he gave us the code from another file, which he took this from, because you guys remember when you're doing the last lab, you had to create a register component in a different file than the actual calculator. So this is just pulling the variables that were already declared in his code. Standard, and then logic. So this is just all copied over, clock, and then reset, and then our input. And then we have standard logic, and then we have data in. So that's like the sum coming in, what's coming into it. And then we have the data out. And by no means do you have to memorize this. He just lets you have open notes on the exam, so that's nice. And so there we go. That's all of our specific port signals that were declared. And we just copy that over since that's declared in another file. For this one, though, vector equals 7 down to 0. And then that is basically what we have. So now we can end the component. That's a specific keyword you guys need to just recall, is whenever you have these, you have to do end component. And now we're going to begin the architecture. So the important thing to take away is, remember, you don't begin the architecture immediately. You have to do your internal signals here, and then you have to do your components as well. Remember that VHDL, it is not basically code at your own free will. It's following a previous template that was already designed, and it is matching your code with that. So you can't write the signals in components in whatever order you want down the line. You have to write them above here before you begin the architecture, because VHDL, it's following a specific format. It's different from the normal coding languages. Okay. So we're going to begin with the control circuit. So this is so I'm just going to make a comment. You use, remember, 2 hyphens to indicate a comment here. So control circuit. And so for a control circuit, this is where we need to do state transitions and state actions. So for state transitions, what I'm going to label this as is finite state machine transitions. And then process, reset, and clock are controlling my process. Remember, whenever you have a process, you need to do begin and end process. Why did I use for the transitions reset and clock? Well, it's always on the active clock edge. And when we turn it on, if we hit reset, that's another one that's going to trigger, immediately go to state 1. And then the rest of the states, it's determined by like the A and C. So here, what we need to do is for specific actions, we need to code how is it going to go from one to the other. Well, that's basically dependent on, like, if reset is 1, go to state 1. And then, so what I'm going to do here, because we're in a process statement, remember, you can use if statements here, guys. So that's the most important part. So we can use if reset, which we have up here, looking here, reset was declared right here. So if reset is equal to, let's just say it's active high, that's what I think he had. If it was active low, then you'd have to put a 0 here. But if reset is equal to 1, And basically then Y is going to be assigned to state 1. Makes sense. You go to state 1 whenever reset is 1. However, for the other else, if, and then this is the active clock. So clock event and clock equals 1. So if it's an active clock, then we need to do is you need to have another if. It's going to be checking if AC is equal to 1, then because AC has higher priority, that's why we're going to list it up here at the top, and then we'll do add after. If AC is 1, then you're going to go to state 1. I'm just looking at this control circuit here to determine. So then you're going to go to state 1. Else if, and let's see, that means AC here, because it goes sequentially, AC must be 0. So then it's going to check out add. If add is equal to 1, then, and then do your statement here, you can do Y is equal to state 2, because that means AC was 0, but if adds 1, you're going to go to state 2. Else, that must mean both are 0, so you go to state 3. Y goes to state 3. Okay, and so now we're going to end this if statement in here. We're going to end the other if statement, and then you're going to end the process. Oh, we already declared that right down here. And so that's how we basically do all this here. Oh, no, I can't do that. So what we did for the control circuit is you have to use this specific line, FSM transitions, and then process, and then it's dependent by the reset and clock. If you hit reset, it starts there. If you hit, if it's the active clock edge also. So if it's reset, you start in state 1, but if it's a clock edge and reset's not activated, then if clear is pressed, since it has higher priority than add, you go to state 1. Otherwise, that must mean clear is 0, so you do addition. So you go to state 2 here, and then else you go to state 3, nothing was pressed, and if, and process. So we did all the state transitions right here. Okay, now we need to look at the data path circuit. And so that's our control circuit. Woohoo! Now we need to do data path circuit. And for a data path circuit, this is going to be basically, if you want to think of what's happening in here. Well, in the data path, I'm looking at this diagram, right? It's going to have to pad with 4 zeros to each of these numbers because the user doesn't input those 4 zeros. The computer automatically does that. So the A 8-bit here, it's going to be assigned. Remember, when you have more than 1, you have to use double quote 0000 and then concatenate. So that means add on to it A, where B 8-bit is going to be equal to 0000 concatenated with B. And now you need to do the adder. And so the adder would be the sum, where we have declared already. Remember up here, going back up, we already have A and B here. We have the, looking for our sum. Our sum is here. It was declared as an internal signal because it's happening within this data path circuit. The A 8-bit and the B 8-bit are internal signals as well. This is where you're, think of it logically, your control circuit, you're going to see more of your reset, the clock, the AC, and the add. So you're going to see more of your port signals, where your data path circuit, a lot of this is happening internally as well. So you're going to see more of your internal signals in here. And then for your register, also you have to, that was declared in another file, but you'll see that is dependent on what you declared here. So some of them, the register is like the mix between the two. So your data path, you'll see more of the internal signals, where your control circuit, you'll see more of the port signals. Just a good, like thing to recall so you don't feel like you're doing it wrong. Okay, so for the sum, it's going to be the A of the 8-bit plus the B of the 8 bits. And now that we have the sum of the two, we're going to have to declare, because if you think about it, our register, we're going to have to do port mapping. You guys remember that whenever you have a component, you have to do port mapping. So I'm just going to say register 1 here. And for my register port map, so the keyword port map here, but first you just declare an instance, and then here this has to match actually what you declared up here for the component. The names have to match, and then you say port map, and then for the register component, basically for my port map here is, remember the register, we had all these specific ports, so we have to match in. So our clear, that's going to be synonymous. If we're looking here, what we have up, we have clear as well. Our load is going to be synonymous with the load we have within the calculator. The clock is the same one that's here. And then the reset, same one up here. Data in, that is going to be our, if I'm looking at this in our data out, our data in is going to be the sum of the two. And because that's loading in the sum into the register and from the addition that was performed in the data path. And then the output is going to be the register out where the LEDs are. That's going to be mapped with the register out pin for that data out. So here, going up, our clear is matched with clear. We declared that in our calculator. Load's matched with load. That's in our calculator. Clock is matched with clock. Reset is matched with reset. And data in, that was the sum from the data path circuit, and data out was the reg out we declared. So that's where we have all those, and then we have to end the behavioral of the calculator. So going back up here, let's just start from the beginning and analyze this real quick. And because that's the important part, what we need to look at. So we need our libraries. The library IEEE here, that's the general one you need to include. That's like your bookshelf, and here's all the books you use from it. And so you use the standard logic. This is just doing all the and, or, not logic. Also, like all your standard logic vectors and stuff, you need that. Standard logic arithmetic, this is because we're doing addition, adding the two together. Unsigned because we're working with numbers. So like if you ever have like a negative number, add with a positive number, you know, like stuff like that, just in case. So you want to make sure you have unsigned as well. Now we're going to look at the calculator. So the ports here are legit copied straight from here. That's what I declared right here. Right here. And then the behavior, this is where my internal signals were. You have to do your internal signals first, and then you do the component, like the register component we had right here. So that's where our one component was from. And then we began the control circuit. So when we began the control circuit, what we did is we had to do the state transitions. We haven't done the actual assigning within here. See how like the clear and the load, we haven't assigned that to the specifics. We'll do that next in the register, but for state transitions, we just copied the control circuit. So it's dependent if you start the calculator or the active clock, and you just run through this whole simulation. So if resets 1, start in state 1, else that must mean you have an active clock edge. If clears 1, go back to state 1. If addition, then go to state 2 and add them together. Else that must mean no change, no button was pressed, go state 3. And then your data path circuit here is where you legit just pad with 4 zeros in front for each of those numbers. And then the sum is the addition of the two. And then your port map is mapping that register component with all the signals you have as your port signals. There you go. So that's basically what you have. And let me open another one because we have to do the register now. And when we're declaring the register, because that's our component, I'm just going to copy all these ports over. So basically, we're not doing any arithmetic inside the register, so I can just copy the 2 first libraries over. But I'm going to copy over all these ports here because it has to be the same copied over from this file where you originally created it. And now what we have to do, remember just, I forgot the entity reg is, and then now I need to say end reg, and then architecture behavior of reg is, and then begin. And here is where your process for your register is going to be dependent upon the clock and also reset. Reset is your asynchronous signal, and your clock is your synchronous one. And then this is where you begin. You always have to begin the process, then end the process. So those are two keywords, just get points for using those. And then remember at the very end, you have to end the behavior. So what we have to do is if the reset is active, then we know the data out, all those are going to be 0, correct? Because if reset's active, then nothing. It's going to go state 1 where the sum is 0. So if reset is active, then data out is going to be equal to, so how do we assign 0 to all those? I usually just do others and then say 0. And if you want to, though, because it's only 8 bits, you can just say 0. 4, 5, 6, 7, 8. Okay, there we go. So either way works. And then else if, and then this would be active clock. So clock event and clock equals 1. Then let's look at this. So clock event and clock is 1. That means at every active clock edge, now it's going to have to determine the register out from those specifics. So looking at what determines the register out here, the only other inputs are the clearing the out to the register. So remember, this is within your control circuit, even the states. So if clear equals 1 and load equals 0, then here, if that occurs, so that means clear everything, load is 0, so that would be data out would be equal, data out is going to be equal to, then we could have 0, 0, 0, 0. Okay. Else if, looking at this, clear is 0 and load is 0. Then no change, so data out would equal data in. Else, the only other condition here would be clear 0 and load is 1. So if that occurs, then you just load it in. So, oh, sorry, here data out needs to be equal data out. And then the other one, if you load in data out, would be equal to the data inputted. So here would be data in. Okay, now that you did all that, we need to end the process here. So I would end the if, end the other if, and then end the process, and then end the behavior. So that's how our register would work. It basically, looking here at the register part, is determined by the reset and the clock, asynchronous, and then if not, then it's on the active clock edge. So if reset is 1, then clear all the data. Else if it's the active clock edge and clear is 1, that means AC was pressed, clear everything. Else if clear 0 and load is 0, then you're going to, nothing changes, so data out's equal data out. And then here data out is equal to data in. That would be if clear was 0 but load was 1. And so the only thing here is, oh, I noticed for my data in and data out, I forgot here as an input, but here for data out, I have to declare it as an input and output. The only reason being because I assign it back to itself. So that's why I have to say in out here. And then my data out here, I would have to also, I forgot to include those in here, just copied over. So that's the important part. Remember, in out for data out, since you assign it back to itself. And that will be your code for this specific finite state machine where you can do an adder. And that was pretty big. Now, the only other example he provided was the bit counting circuit. So I'm going to do that just because he probably is going to test on one of these. We don't know which one, so it's better to be comfortable with both. And so let's look at that one. So I'm going to go back and share my whiteboard. So let me stop and then reshare. Okay. So for a bit counting circuit, what do we need to do? Bit counting. We need to count numbers and count number of bits that are 1 in register A. And so what that means is it's just going to count how many like have a 1 value and then all the others are 0. So that's what it's going to do here. So the other one, it is going to store the count in B. Okay. So within our bit counting circuit, it's going to just count all the ones and it's going to put that count in B. And so what we need to know now is, remember from the last one, you had to do an algorithm. And then what we're going to do is, to start off, you're going to initialize count B to 0, correct? Because you want to start the count at 0. And so then you're going to check. So you're going to move from the, you're going to check the digit on the very right. So that's the least significant bit, like the one on the very right, like 001. 1 would be the least significant bit of A for 1. And increase count B if necessary. And then right shift A, where you're gonna, so that move everything over 1. So shift in left bit of 0. You don't want to shift in a bit of 1 because then that will make it count an extra 1 that wasn't originally in the number. So that's why we're shifting in 0. And then if A is equal to 0, stop since no more 1s. Otherwise, if there are still 1s in there, you're going to check then the least significant bit again, and then go through and right shift and then check, are there any more 1s, then keep going through. And then you're done basically once that number A equals 0. So here what's going to happen is we have actions. So you're going to first initialize the count, and then you're going to check here. So you check and then you do the right shift and then you might stop. So here it's all in 1 because there's one action of right shifting. The others are just checking and seeing if this is true, it's conditional. Then you're done here. So those are the 3 states. So we have state 1, we have state 2, and we have state 3. Okay, now that we have the 3 states, what we need to do is we need to say that the signal S equals 1 to indicate new data available on A. So that means start counting S equals 0 to indicate data is not ready on A. Okay, so what we need to do is let's just create our chart and let's see how this goes. So let me just try and see what's going to happen. So for ASM chart here, I'm going to do it in a different, so ASM, let's make it blue. ASM chart. Okay. So what we're going to do is, remember, we always start with reset and then usually it's active high here. So I'm going to just have reset. And then I'm going to have my 3 states. So I'm going to have 1 here, for state one. And so within state one, that's like the beginner state. And so that's initialize B to 0. So B is initialized to 0. So we can just say B is 0. And then what's going to happen after that is it's going, remember, with her diagram, initialize B to 0 and check the least significant bit of B. So here, what's going to happen is when it's going to check the least significant bit, it needs to see is the data available or not. So if the data is available, then it is going to do its checking procedures. So to indicate that the data is available to check, you have to state here, you have to have S. That's going to be a conditional. So if data is available, then it will continue. However, if it's not available, then it's going to return to the starting state and just nothing. Basically, it's just going to go back to the reset. Nothing's going to happen until data becomes available. And then if there is data available, it's going to go down and it's going to right shift it over since it performed the operation within it internally. And so it's going to shift the data over one since it checked. And what happened is, let's see, why would it shift one right before checking if there's no more data in A? Let me see real quick. Data available on A, start counting. Okay, the reason why is here. You start counting when there's new data available. And so we're going to start the count. And when we start the count, it's going to shift in a 0 to the number and it will right shift. And if there's no more data in A, it's going to check. So let me draw it out. So it's going to start with right shifting 0, right shift A. And then it's going to go to next box where in this box down here, it's going to check. And this box is a little different. It's going to see if there's no more data in A. That's what this one is checking here. When he did it, I was a little confused. He put a question mark over here. So if A is equal to 0, that means there's no more ones in it. However, if that is false, that there's still more data, it's going to go down here, and within this, it's going to see, do the checking for us, and it's going to check if there is more data in it. And so what he did to signify that is he did this, he used a lowercase a here, and so it did A of naught, and so let me take that in here, A of naught. And then what he did is he put, if that is false, then you're going to go back up, but if it is 1, then you're going to add 1. So this is A of naught is checking the specific digit. So let's run through this again. In the beginning, we initialize B to 0. Here, it's going to start the count if that is available. So we right shift A, and then because what's going to happen if there's more data available, it's going to go down here and it's going to check if that least significant digit, A of 0, is 1. If it is, then we're going to see it needs to go to another condition, where in this condition, it's going to add 1 if that is true. So B equals B plus 1. So that means the least significant digit had a value of 1, and so it's going to add 1 to the count. And then going back up here, it's going to right shift it over 1 again because we just counted. And we counted the least significant bit, so you can shift it over again. And then it's going to see, is there any more 1s in the number? If so, then go through and check. If that least significant bit has a digit of 1, go here. However, if that least significant bit does not have a digit of 1, then it's just going to go over and it's going to shift it. And so here it's going to go back up and then just shift right one. And so it's not going to add one to the count. And then if there, from this box here, if this would mean that there is no more ones within the number, because this would then become true. So let me, if it wasn't true, there was one still in the number, but if this was true and there was one still in the number, then it's going to check out, this is true. And so then there's no more ones in the number. Sorry, let me just make a text real quick and edit. Checking if there are any ones in the number. And so here, that's what's happening within this small box here. So I'm just going to label that. So within this A question mark is 0, that's what it's doing. And so if there are not any ones in a number, okay, are not it. So if there's no ones in the number, that means that we have finished and we can go up here, and within this state 3, that means we are done. There is nothing left to count. And so this is where it is done equals 1. And then it's going to go back and it's going to see if there's any new data available, then it will start the count again anew and it will repeat the process. And that's what we'll see up here. But if there's no data available, it's just going to remain in the done state. And so that's why it would go here. So going down, it will just remain in this state here. Okay, but if not, if there is now data available, it's going to clear the previous count and it's going to go up here. So if there is no new data available, but if there is no data ready on A, it is going to wait until there is data available. And so now what we do is, let's repeat this. So walk through it all at once, because I feel like it was confusing a bit, especially for me even understanding how this works. So we start with the ASM chart where the reset, that's the button. So when you start it up, it's going to start with 0 for the count initially. It's going to see, is it ready to count? If so, go to shift it over 1. If it's not ready to count, go back to state 1. Here, it's going to check if there's any ones in the number. So if there are not any ones in number, if there are ones, then it's going to check if the least significant bit is 1, then it's going to add 1. If the least significant bit is not 1, it's going to go 0 and then repeat the process shifting over. However, if there are not any ones left in the number, then it's going to go here where done is 1, and it's going to check to see here at S, it's going to see if it's 0 or 1. This means that there's data not available. So it's going to go back to the state 1 where it's going to be set at 0. But if the user has not triggered to do a new one, it's going to just remain in the done state. Okay. So for this one, for a data path circuit, it's going to determine what we need here. So we definitely need a counter because we're adding one every time, and we need to shift it over. We're doing right shifting. So for a data path circuit, I'm going to erase this on the left, or I'll draw it actually down here. So for a data path circuit, we have a counter E, and then we have a shift register, which we'll label A. Both of these are going to be doing, the counter is going to be adding 1 every time, and the shift register has to shift it over the number. And so when I draw out this data path circuit, we're going to have the shift register here, and I'm just going to have the counter over here. Let me make this one actually. So shift register and counter. Okay. And so I'm going to label each of these. So this is my shift register. shifting right. So I'll just call it shift right. And then the other one I'll label as the counter. So this is B, this one is A. Okay. Now that we determined that, we can label all of our ports. So within the shift register, we're going to have a few inputs to that. So we need to make sure. So we're going to have our data coming in, and we're also going to have any serial input. Remember, that was like our S. So like S can be 0 or 1 if data is ready or not on the register. We're going to have our loading. And so remember, with a register, you have to have the enable pin as well. And then we're going to have our clock signal here. So you're also going to have your clock. Okay, on the output, you're going to have Q. You're also going to then have it checking if the number is ever, no more ones are in the number. And then the other one you're going to have for your counter, it's going to start at 0. You're going to start with the initial count. You're going to load into that counter. The B initially is 0. And then what's going to happen down here is you have to have an enable pin for this one as well. And then you have to have a clock signal. And then the Q for the output, you have to have determined, and that will be for your counter. So for all those coming in, we're going to draw the specific inputs, the data coming in, and then initially set to 0, and then load, and then enable pin, then the clock. Oh, that can just represent my clock signal right there. And then the clock, active clock, positive edge triggered, and then LB loading coming in, and then the enabling, and then loading in zeros for all the values. Then my outputs here for Q. Okay. Yay. Okay, we got all that. So for our data, it's going to be with n bits. And so I'm going to label that just here in another one. So we're going to have n bits. So let's say we have a number that is like 20 bits long. So that's what our n would be. N is 20. And then here, this is our W for serial input here. So determining if that is ready or not. And then our load here, that's what we have here, where our enable, we have to have an enable for the register, then our clock, and then over here we have load enable. This one, to determine how many, it's log of base 2 of n. And the reason being is because the amount of bits you have in here, if you have 3 bits, that means you have to count up to 8, correct? And so because 0, 0, 0, 0, 0, 0, 1, all the way up to 1, 1, 1, you have to count up 8 times. So that's why we have this log 2 of n, because that determines how many bits you have in order to count. And so to count from 0 to 7, you would need like 3 bits, or that would basically be it. And then your output also for the counter to represent is going to be in that bit notation as well. So log base 2 of n. Okay, and then what we're going to have here for our output is it's going to be checking if there's any ones left inside. If there's any ones left in, then it's going to then keep counting. But if not, it's going to stop counting. So oops, let me draw that gate better. We're going to have a NOR gate here. A NOR gate, it checks if there's any ones left in there. Basically, it's the reason being is for an OR gate, it checks if there's any ones. If there's any ones, it's true. And so then that would produce what we want. And so here they use a NOR gate, they NOT it. And this is because when A is all 0, that would be false. And so this would produce Z equals 1. Because when they're all false, then Z is going to be 1 when A equals 0. Okay, now that we determined that, because if A was all 1, 1, 1, 1, 1, that might cause an issue. So that's why we have to use the NOR gate here, because the NOR gate specifically responds. Okay, and now that we got that, we'll have to be always checking here that least significant bit. So that's why he represented it with A of 0 for n bits. Okay, now that we have that shift register, now we are going to go to the operation and control signals. I feel like the control circuit is more what I understand from this one. I hope he asked just on the adder because this one's a little weird, and that's what I feel like he's going to make us do, but we'll see. Operation and control signals. So for operation, we're going to load data into A, and for the control signals, that is going to be LA equals 1. And then for the next operation, if we shift right A, that's going to be enable is 1. If we set B initially to 0, that means that LB is equal to 1. And then for if we add 1 to the B count, that means that EB for other enable pin is going to equal 1. And then A equal to 0, is it or not? Are all the pins? If it is, then Z is equal to 1. So here, what we need to do is we have to relabel the chart, and this is where it makes more sense to me, at least. Load data into A. And so if we're thinking about that, that happens actually in our data path circuit where it loads in the data. And so then our next one for shifting right A for the EA equals 0, that's where it actually occurs in the control circuit here. So this is where E of A equals 1. Okay. Then our next one where we set B initially 0, that's where LB is equal to 1. So we can cross this out here. And then looking at our next one, EB is 1 when we add 1. So here I can do EB is equal to 1. And then is A equal to 0? Checking. This is where we set Z to 1. So I can just write Z here. Because when I just put Z, it means Z equals 1. If you use the book notation, I can put Z equals 1 though too. Whichever one you guys want, you can just put it as Z though. So we relabel the ASM chart to get our control circuit. And now we need to determine our port signals and our internal signals from this. And so when we determine our port signals, what we have, let's look at it. Well, what does the user need to see? That's the most important question. So for port signals, the user is going to see, let's look at it. Okay, the user is going to have to put in the data, right, for A. They're going to have to determine if we start loading in the value for A, loading in that data. And then that clock, remember, that's the weird one with the FPGA. The user has to read how many bits are high. And so this is where B is coming in, where B is labeled here. That's the output of the counter. So that's the user reads the output. And then the reset, the user can reset when they turn it on. S, that is, the user says that the data is available or not. So they push the button either to indicate data is ready and done. The user needs to know when the circuit has finished counting. So it has to see the done signal. The internal signals, on the other hand, are EA. The user doesn't control when it shifts right. A, the internal signal that the user does not see happening within the shift register. And then Z, that is basically the internal user doesn't really care about that condition where Z equals 1, checking if there's any ones left in it. LB, that is loading it in, and EB as well. These are just for the counter that happens internally. Then Y is the states. Okay, now that we have determined that, let's look again. So let me just match these to the actual circuit and see if that makes more sense for you guys. Data for a port signal, the user has to put in the number that is going to be counted. LA, loading in the number, they have to load in to indicate that they're loading. Clock, the clock is, remember, that's the weird one internally with the FPGA. B, the user has to see the output of how many counts there were. Reset, the user push the button if they want to reset it. And then S, that is saying if the data is ready or not. And then done, that is if the user needs to see when it's done counting. EA here for enabling, that is on the counter. User doesn't care about the counter as much. A is corresponding with, let me make sure I got this right. A is corresponding with this output right here. And so from Q, and so the user doesn't care about that one because that they only care about when it says that it has done counting. Z is going to be the one to indicate that it's done counting, so user doesn't care about that either. This is just the counter, all the internal signals and all the states. The user does not care about that. Okay. Now from the code, we have to go through and determine how to write this code. And so this is a little bit different. And so he provided this code. So let's walk through it. So let me stop sharing real quick. And let me reshare with the actual code here. So let me open that up. Okay. Sorry, I have to share the actual code, so give me 1 second. Okay, here we go. So let's go analyze this. And let's see. Oh, let me go back and take a screenshot of this so we can compare side by side. So let me real quick take a picture. Okay, now let's start sharing this one. Okay, so we're gonna have the code here on the one side, and let me just delete this. Don't save. Don't save. Here we go. Okay, so now we have our code here, and let's see how the VHDL wants it coded specifically. And so when we're looking at this diagram on the left, it includes all of our libraries for the bit counting circuit. So library IEEE, the standard logic library, and looks like they use this work and work components for the shifting register. So these are for the shift register here. And so entity, they called it bit count is, and then they had their port signals here, the clock, the reset, and LAS done B, and that was pretty much all their ports there from the port signals. They literally just copied from these here. And then they ended the bit count, and then the behavior was the internal signals they had here. They had Y as the state type. They had 3 states. They had their A, standard logic vector, 7 down to 0, because they had a 3-bit number. Then they had EA, LB, EB, and it looks like they used low here. And it looks like for low, what they used instead, when I'm looking at this, they have Z, they have EA, they have LB, they have EB, and they have Y, and they have A. Oh, that's funny. We didn't have low in ours. He must have had that somewhere else in his when he declared it. Okay, let's just keep going and see, and then we'll find out what was different. Okay, so it starts at the transition. Same thing as we did with the adder. You declare the internal signals here. He didn't have any components, so he just began the architecture. So for the transitions, it's on the reset in the clock, the asynchronous signal in the clock if it's positive edge triggered. If reset is 0, then it starts in state 1. If it's positive edge triggered, then for case Y, if you're in state 1, then if S is 0, then you start in state 1, else you go to state 2. And then in state 2, if Z is 0, oh, sorry, I think here it should have, looking at these states here. Yeah, okay, that makes sense. So look at the diagrams here. In state 1, if S is 0, then you're going to go back to state 1. If S is not 0, then you go to right shift A in the state 2 here, the state 2 block. And then in state 2, if Z is 0, then you're going to go down to state 2 here because it's going to return here. But if Z is 1, then you go to state 3. In state 3, if S is 1, then you stay in state 3, else you go to state 1 back here. And then they end the process. Then here for the outputs, for the finite state machine outputs, this is dependent on Y and looking at also A of 0. And so we begin if enable 0, LB 0, and EB 0, and done is sign 0. And then we start with the case Y to look at all the different states. And this is based off our internal signals here. We labeled for state 1, state 2, and state 3, what we have written inside here. And then for the data path circuit, they basically just go through what we've written here. So if reset is 0, then B is initially going to be set to 0. Like we said here, if reset, B is initially set to 0. And then if active clock, and then we check if LB is 1, so enable on the counter is 1. And then sets B initially 0, but if EB enable on the counter is 1, then it adds 1 to it. So we see EB here. If it's 1, then it adds 1. Where if LB was 1, it's set to 0. So this is just where all the control signals are taking place. And then it shifts basically in the data path circuit. And then that is what happens then if Z is 1 when A is all zeros, then it's going to display a 1 for the output, but if not, it's 0. So that'll tell the user if it's done or not. And that is all that circuit. So that will be the whole review for the final. That was everything he said. Basically what he wants you guys to know in digital system design is you start with an algorithm, you do a data path circuit, a schematic, you do operations versus control systems. You do the control circuit, and then you inspect the data path and control circuits to find the port signals and the internal signals. And then you do the VHDL code where you start with the port signals and you do the transitions for the finite state machine, you do the output, and then you do the data path circuit. And then once you get those signed, then that's pretty much it. So what you guys just need to know is the finite state machine analysis. So working backwards, the ASM charts, how to design those. In digital system design, I would say focus more on the adder. This bit counting circuit was a little bit weird, and I feel like he's not going to test me on it because our lab was on the counter as well. Hopefully that helped. I will stop the recording.